All right, hello and welcome to this webinar on CLT using FEM-Design. My name is Isaac and I work with business development here at StruSoft. And this webinar will be recorded and all example files will be sent out to all participants after the webinar is finished. I also would like to encourage you to ask questions during the webinar by using the GoToWebinar interface located at your right-hand side, and I will get to them at the end of the webinar. Should there be any issues with the sound or the picture, please just write to me in the questions formula in the questions section, and I'll keep an eye there just to make sure that you can hear me well and see what I'm sharing. So let's begin just with a brief introduction of the different modules that we're going to use. Sorry, that's the wrong one. The different modules that we're going to use today. We are using 3D structure, which is the main modeling and analysis module for FEM-Design, as well as timber design, which is design of timber according to Eurocode. That is for bars like columns and beams and so on. And also CLT design, which is a separate module for CLT. And it is according to Eurocode 5 and some additional checks according to relevant literature. I will go into a little bit more detail about this very soon. I will start out by just walking through some theory background, and then I will continue doing modeling, results, design of CLT, and at the end, a little bit about documentation. So let's go into the theory background. So first of all, we have implemented a specific shell element based on the laminated shell theory. And this shell element is different compared to the normal orthotropic shell elements. And in the top left corner here, you can see the stiffness matrix for this laminated shell element type. And the thing that is different compared to the normal shell is this B matrix, the B notated in this matrix. So you have one part over here and one part over here. And that is normally called like the coupling matrix, which connects bending and axial deformation in the element. And I would like to demonstrate this first in FEM-Design. So let's jump over to FEM-Design. And if we take a look at the structure tab, we can open up the settings or the properties for the timber plate by going into timber plate, selecting the question mark and selecting a plate. And here on the material tab, we can change the mechanical model from being orthotropic shell, which is the normal shell element, to cross-laminated timber or general laminated composites. And when it comes to the cross-laminated timber, we can see, sorry, let's open up this again, and we can select the one that we assign here and click on display stiffness. And here we have the flexural stiffness matrix denoted by D, the membrane stiffness matrix denoted by A, shear stiffness matrix denoted by S. That's just as a normal orthotropic shell. But the thing that differs with this laminated shell theory is the eccentricity or coupling stiffness matrix denoted by B. So let's go back to the PowerPoint presentation just again to show you. Here we have the D part, A, S, and the B coupling matrix over here and here. So what happens is that if we load this with an in-plane force, that's the only force that is applied on these two shells. So we have an in-plane axial force applied centric to this. You will get bending in the shell because of this coupling between axial deformation and bending. So this behavior will, of course, potentially influence the load distribution in the structure, and therefore it is recommended to use the laminated shell theory when modeling CLT panels because it's a better way of modeling the behavior of CLT, especially if the CLT is eccentric or doesn't have the same number of layers in both directions, compared to just assigning the stiffness as an orthotropic plate. I hope that was clear. So that's the first part of the theory. The second part is regarding the Eurocode limitations. So we have implemented some design checks for the CLT in the software, and that is for tension and bending, that is according to Eurocode, compression and bending according to Eurocode, shear checks according to Eurocode. But then the Eurocode, since it's a little bit older and isn't really complete when it comes to CLT, we have some additional checks. And these additional checks are for shear interaction, tension and shear, compression and shear, buckling. And in addition to this, we also have fire checks. And it's based on the Eurocode method of calculating a burnt section for timber, but it's also using some other literature to make it conform with a CLT product instead. We will take a look at the different formulas for this during the design phase, but it's very important to note that it's not only Eurocode checks implemented in the software, but also some additional checks according to other literature. And these are also optional and will show up in the calculation parameters for the CLT panel. So if you want to disregard these additional checks, you can uncheck them and just perform the tension and bending, compression and bending, and shear according to Eurocode. If we continue to another part, an important part when it comes to CLT is the reduction factors. So when defining a CLT, you have the possibility to assign different reduction factors, and these are product specific depending on the different manufacturers and how they, basically based on tests and other procedures that they have when they are creating their CLT. And you can see in the stiffness matrix here the different positions where these reduction factors are applied. So when it says like reduction factor R33, that means that this reduction factor is placed in the overall stiffness matrix in position 3, row 3, column 3. And the same for R66, R77, and R88. When we look at the modeling part, I will get back to these reduction factors and show how you can insert them into the software and for that specific product. The last thing that I want to highlight when it comes to the theory, it's an option when it comes, either you can select to have glue at narrow sides or not. That is, if you want to glue it at the edge of each board in the blue shade in this above picture here. If you apply glue here, you won't carry out an additional torsion check, but if you don't have any glue there, there will be an additional torsional check for each layer in the check. Another option is to have a shear coupling, and that is normally always the case. The shear coupling is between each plank layer in the CLT panel. In here we see it illustrated by the light green color. And if you don't have any shear coupling, each layer will work individually without any shear connection between the different layers, if that makes sense. So I will just very briefly show this in the software as well. So let's jump over to the software, and I have some other examples over here. Let's see here if I, oops. Sorry, I was on the wrong screen. Okay, so let's start out with the shear coupling. So on this left-hand side, we have shear coupling on, and on the right-hand side, we have it selected as off. And this is a setting you can find under the definition of the timber plate. If you go into the material tab and you have consider shear coupling between layers. And if we take a look at the other one, we have this option deselected. If we go to the analysis tab and take a look at the stresses in the CLT, and we take a look at this with shear coupling on, we can see that we have a shear distribution that goes from positive to negative for it's connected, so it's working as one unit with the neutral layer in approximately the middle of the CLT. So the top part of the CLT is under compression and the bottom one is under tension. Compare that to the other option where you don't have any shear coupling between each layer. If we take a look at the other one, you can see that each individual layer goes from compression to tension. So that is each layer working individually without any shear coupling between the layers. This is normally never the case unless you're maybe checking a very specific accidental loading situation, or if you're doing maybe you have another type of composite that doesn't have any shear coupling between the layers, then this option could be valid. But for normal usage, you should always consider this shear coupling between the layers. The next option is about no glue at narrow side or glue at narrow side. So if we go back again to the settings menu, we can take a look at the other option here. So we have no glue at narrow side checked for the left one and unchecked for the right one. And this will influence the design checks. So if we go into the timber design for the CLT and we take a look at the utilization and the formulas, let's just carry out the check real quick here. I will go into the utilization result and click on the magnifying glass to obtain the detailed result for each object in the model. So I'm just right-clicking here to open up the formulas. So when we don't have any glue at narrow sides, this additional check for torsion is carried out for this CLT panel. But if we have glue at narrow side, this check is disregarded. So now we don't have any check for torsion. So I hope this was clear. If you have more questions and want to go more in depth with the theory behind the laminate shell theory and the feature in general, we have a comprehensive handbook for the CLT module that you can read and find on our wiki. But let's continue to the modeling parts. And I just want to highlight 3 different options here. When modeling CLT, you can either choose one CLT panel from the existing library, you can create your own CLT, or if you have another type of laminate, let's say maybe you have some kind of glass laminate or maybe plastic or something like that, you can use the method and have a general laminated composite, which you can build up with any material basically. But when you're using the general laminated composite, you cannot perform design, but you can get the forces and the moments, the forces between the different layers and so on, and carry out a design manually if you want to. So I will go through these three different options in the software right now. So let's go back to the structure tab, and I will find the CLT or under the timber plate or timber wall feature. And let's go into the default settings and go to the material tab. So here again, we can select either the orthotropic shell, which is the basic normal shell without any coupling. We have the cross-laminated timber, which is for CLT, both analysis and design, as well as the general laminated composites. So for the general laminated composite, we can build up our own composite by just defining a material name, some material properties, and just perform a analysis of this. But let's define a new CLT. So we have our library here different types of manufacturers. And if your product is not included in this list, you can create your own CLT according to the datasheet for that manufacturer. And you can do that in multiple types of ways. An easy way of doing it is to base the CLT on an existing CLT. So if I select this one and click new, I will get this 105S as the base layout, and I can make changes to this. So in this window, I have a drop-down list here where I can define the mechanical properties for each layer and also the limit stresses for each layer. And if I double click here, I can select a material from the material library. So that's normal timber materials. But I can also make changes to the properties, like for example, the elastic modulus, shear modulus, and so on. I can also set different thicknesses here and also set an angle. Normally, this angle is always 0 or 90 degrees, but it's a general theory, so you can set whatever angle you want here, basically. But for now, I don't know of any products using anything else but 0 and 90 degrees. But maybe it will come in the future. Who knows? It's the same on the limit stresses. You will get, if you select a material from the library, you will get the default values for that material type, but you can of course make changes here as well if you have a specific material or maybe want to reduce the properties for some reason. When it comes to reduction, we have a KDEF value, and this is the default KDEF value that will be shown when you select the different service classes. So for service class 1, I can set a KDEF, for service class 2, another one, and for service class 3, another one. And when I select the service class over here, this will be the default value for the quasi-permanent and frequent SLS, but I can overwrite them if I want to. But this is just the default value. So let's say that I change this to 1, 2, 3, just to make it clear for everybody to see that it changes. And I create this new CLT. I have many tests apparently. Okay. So now when I select number 2, I will get KDEF as 2, number 3 KDEF as 3 as the default value. But I can of course overwrite this if I want to manually. It's just the default value that is assigned here. Then we have the stiffness reduction factors that I've talked about before. These are R33, R66, and so on. And these are product specific, so I would recommend you to take a look at that specific manufacturer and see if they have reduction factors in for their products. Sometimes they actually place the reduction factors inside of this table instead of having it here. It's a little bit different depending on the manufacturer, but in general, most of them have some kind of reduction factors that you should insert according to their data sheets. Okay, so when we have created a CLT or chose one from the library, we can set the different KDEF values that we want if we want to be different than the default values depending on the service class. And we should always take a look at the consider shear coupling and no glue at narrow sides. These two options are not product specific, so you have to check with the manufacturers to make sure if they have glue on narrow side or not for their specific product. That is not included in the library because it can vary a little bit depending on the batch and basically what you decide together with the factory. So especially this no glue at narrow side, it's important to consider and check when you're picking a CLT and not only go with the default value, because the default value, it's not included in the default value, if that makes sense. When you've selected a CLT, you have to select the main direction. by drawing a vector, and then you can define the CLT however you want. And that is how you define or draw a CLT. And this direction can, of course, be in a skew direction if you want to. So it's important to keep track of the main direction. So this arrow here will define the X direction of the CLT panel. All right, so let's take a look at the results also from the analysis. So when you have assigned a CLT, you can just carry out a normal calculation. Since it's a finite element software and it's just a stiffness, you can carry out a stability analysis, eigenfrequency, footfall, yeah, basically whatever analysis you wish to carry out. And the CLT will be included in that analysis. It can also be nonlinear with connections and so on and so forth. And in general, when talking about the CLT, it's important to mention that connections are quite important to take into consideration. So let's just showcase how you can do that real quick. So in general, you have specific stiffness reduction for some of the limit states according to Eurocode. I think it's like 2/3 of the stiffness in ULS or SLS. So you have one stiffness valid for ULS and another one valid in SLS according to Eurocode. I think it's like 2/3, a factor of 2/3, something like that. And if you go into the edge connections for the plates, you can find under the data tab the settings for that edge connection. So let's say that you have calculated the stiffness to be like 500 or something like that for this type of connection. And maybe it's a hinge connection, so this should be 0. Now you have the possibility to uncheck this same for all calculations, and you can assign another stiffness or another reduced stiffness for another situation. And let's copy this into every one first using the copy tool. So we get the same one all over, and here we can make changes. Maybe we want to, this is, actually I think it should be higher, sorry, maybe 700. That's just an example. And we can copy this to the other SLS situations. And if you're using a common connection that is repeating in the structure, we always recommend you to create a type instead of using the custom type. You can go into the edit library and you have the same settings here, and you can name it to something. And you go through the same settings. You can have different stiffness for different calculations, and this could be then visualized in the software. If I select this type instead of a custom, we will get, let's select another type on this side just to make it clear. We can go into the colors tool. If you go into tools and colors, and we can go to the edge connection rigidity type. And this will actually give you different colors for different types of connections. And this is a good way to keeping track of the different connections available in the model. And of course, you can also display this text if you want. So if we go into the shell properties, and we can display, under the connections and type, and it will also write the type in the 3D view, which makes it even easier to follow. Now let's continue with the results. Let me just open up this again. So it's important to keep track of the different coordinate systems when working with CLT, because we have 3 different layers of coordinate system. So we have a global coordinate system, which is basically used for different types of supports and so on. Then we have the local system for the shell, for the CLT shell. And then we have a local system for each layer. And this local system corresponds to the angle of each plank layer. So in this case, it's like 0 degrees, 90 degrees, 0 degrees, 90 degrees, and so on. So when we take a look and look at the laminated shell stresses and select, for example, von Mises in the center of each layer, we can select the coordinate system, either the shell local coordinate system or layer local coordinate system. And then we have different layers. So in this case, we have a CLT containing up to 7 layers in this model, and we can select a specific layer and display this result. Let's show all the different CLTs in this model. We can take a look. So now we're looking at the sigma von Mises stress in the center of each layer for layer 1 according to the shell local system, if that makes sense. And this is maybe a good way to find like max and min stresses, but often you want like a section where you can find you can see a section drawing of the stress distribution over that section in that specific point. And you can do that by going into the detailed results. And here you can select a specific point and get the stress distribution in that specific point. So in the picture here, you will see the point that is selected and the different stress components like the sigma x, sigma y, tau xy, tau xz, tau yz, and these corresponding stress distribution here. However, this is also just in one point, and often you're looking for the maximum and minimum stresses, and then you should go into the result called maximum of load combinations. And here you will find each stress component maximum for all load combinations. But if you select a result here and go into the detailed results, a new button will appear called Select Laminated Shell. And this will actually automatically find maximum and minimum points for the different stress components. So here, instead of selecting a point, I'm selecting the entire CLT panel, and the software will find these different points that gives, in this case, all components a maximum. So here we can see that the sigma x point is in the middle of the span. Here we have the maximum value for this component, which is 8.3, and for example, here for the tau, we have 0.3, which is at this edge, and we have the maximum here. And if I want to find the minimum instead, I can just find all components negative or find a specific stress in a specific layer or in all layers. So let's say I want to find this sigma maximum, or maybe just in layer number 1, sigma maximum, and so on and so forth. So there are many different possible filtrations you can do using this maximum result. But please keep in mind the coordinate system of the local shell and the local layer. Yes, so let's continue to the results part as well as the design. Sorry, I just went through the results. Let's continue with the design. And I want to highlight just a few ones that I want to walk you through today. The first one is we have a normal ULS check, including buckling check, which I will demonstrate, as well as ULS accidental, including fire design, and also some SLS checks that can be a good idea to take a look at. In this case, we have deflection and eigenfrequency calculation. You can also add to this if you're doing a CLT floor, maybe footfall analysis, which is included in the software as well. So let's jump into another model, which is a CLT building, residential building, as an example. And let's take a look at the results. So first I want to go through the deflection check. And the deflection check can be found under the analysis tab, since the deflection is not really material dependent, it's just a deflection. But what is nice when using the deflection check compared to just viewing the result called translational displacement, for example. The translational displacement is the total displacement of the entirety of the model. So let's take a look at this point, for example. Over here, we have actually some kind of axial deformation in this column row, like 0 point something millimeters. And this shouldn't be included in the deflection check because it should be the relative deflection of this balcony. So you should actually subtract the deflection at the edges of this plate to find like the maximum deflection, or at least at the supports of this plate, if that makes sense. And that is exactly what the deflection check is doing automatically for you. It will also calculate the deflection limit for you. So let's go into first the cogwheel, which is the setup for the deflection check. In this case, you can select which load combination you want to carry out the deflection check for. This can be multiple. You can select multiple ones if you want. But in this case, I'm only doing the deflection check for the characteristic load combination. Then we should define the different deflection limits. And you can find those under the shell deflection region as well as for bar deflection region. So this tool is available both for bars and shells. In this case, it's a shell mainly. So let's go in here and we can see, let's take a look at the first story. Actually, let's take a look at the story number 3. So here we can see that the software has automatically divided this into different regions. So you have 2 different arcs for each region, defining the short edge and the long edge. But you can divide this further into different parts using the pen and just selecting a shell and selecting a region. So let's say that I want to have this region instead. I can do it like this. But let's just undo that and go back. We also have the properties for the different regions. So in this region, we want to check deflection, or you can check rotation if you want to, or if this region is not relevant for the deflection check, you can do that as well. Let's select the deflection. Then you have at the bottom here some deflection limits for the characteristic combinations. You have a relative limit. You can set L divided by something, and if you want an absolute limit of 30 millimeters in this case. And the L could be manually defined using the user-defined length, or you can set the shortest edge of this, which is the shortest arc length here, over like this, or the longest edge, which is the other direction. And the software will automatically then calculate the relative limit for the deflection. When I've done this, I can carry out the check, and I've already done that. So I click on the check mark here, and I select either shells or bars and click on check, and it will run through all the different regions and calculate the relative deflection for each region and compare that to the deflection limits. And this will give you a new result called deflection over here. Here you can go into the maximum of load combinations to see the utilization. So here we can see the utilization as a color palette for that load combination. In this case, it's the the characteristic SLS. And if we take a look at the value, you can see the value of the deflection, and this is the relative deflection. So let's just take a look here at the edge of this slab. You can see that there's a value of 7.35 millimeters. If we instead go to the global deflection and compare that, we have a deflection of, sorry if I just grab the correct one here. I should select, sorry, I'm in the wrong load combination. I should select maximum of load combinations in the set direction minus and the characteristic display this. Okay, so here we have a deflection of 7.74. I think that's the maximum. Yeah, 7.74, and compare that to the relative deflection, which is 7.35. So it's a little bit different, and that's because the relative deflection is subtracting the deflection at the edges or at the supports for the slab. So that's a neat feature, I think, to calculate the deflection checks without doing a lot of manual work or actually overestimating the deflection, because the entire structure will deflect a little bit. Let's move on to the normal ULS check. We go into the timber design, and we can select from the design selector the CLT panel here. And let's also view the entire model. I've performed a check for this for these CLTs, and because I also carried out the deflection check before I did the I also carried out the deflection checks, it will also show up in this table. So at the right hand side, you have the deflection utilization for each slab. I also created some different groups, and I have a plate group, roof group, and so on and so forth. And when you're doing an auto design, you can each member in each group will have the same section. So it will take like the worst case for that group and design. However, the design won't take into consideration the deflection. So the deflection needs to be handled manually somehow. It will only take into consideration the other checks for the ULS. But if you have defined different groups, you can actually set different utilization limits. So let's enter the plate groups, for example. And here I can select which type of CLT I want the software to choose from, and I can limit the utilization to, for example, 50 or 60%, something like that, because normally that would probably give me a reasonable section. If I set this to 100%, I will almost never be able to fulfill the deflection limits as well as the eigenfrequency. So it could be a good tip to set this to like 50 or 60% as a starting point to select like the initial section, and then you can carry out some additional checks and look at the deflection a little bit, and also the eigenfrequency and other SLS checks that you may have to carry out, for example, acceleration and so on. So let's take a look at this wall over here and do a design of this wall. So first button after the design selector is the buckling length. So here I can actually define a buckling area, and here I decide which direction it should be, like the local x-axis of the shell, local y, or in a skewed direction. In this case, I want to check the buckling between the window and the door. So I can select, it's the local x in this case. I select the shell and I can draw a section or an area. And then I need to define a beta value valid for this area, let's say like 0.7, something like this. And now it will carry out a buckling check of this area. In this case, it's quite a thick area, but it could be like beside an opening or something that is larger, and could be valid to check for sure. The next option is the calculation parameters. And if you go into this, it's settings that is for each, it's object specific. So the setting is for each individual object. You can have different settings for different objects. So let's go into this object and take a look at the options. So here we have the shear interaction formulas. This is the additional check in addition to the Eurocode checks, and that's the reason why it's optional, as well as the torsional check if it's carried out, if you don't have any glue at the narrow side. Then this is also an optional check yet that is by default carried out, but you can disregard this if you want to. Also, you have some reduction factors for the material properties when you're carrying out the buckling check, as well as a beta C value. And that is also for calculating the buckling, but it's not the beta value, it's another value in the buckling formula. We can take a look at that later. Okay, and that's the settings for the check. And now I can just carry out a check and just right click on this member and check that for that CLT panel. As usually in FEM-Design, you can reach all formulas by going into the utilization results, going into the magnifying glass, and right-clicking on an object. And this will give you step-by-step formulas for all checks in the software. So also for the CLT panel check. So here we can see the different Eurocode checks. So you have the reference to the different Eurocodes sections, as well as the shear interaction, torsion and shear, compression and shear. And since we have selected glue at narrow side, there is no torsion check. However, we have defined a buckling area. So here is the buckling check carried out by the software. So here we have the beta C value, and it comes in to this K factor, which is basically a reduction factor for the material, you can say. So in this case, it's actually the buckling that is the highest utilization. However, the utilization in general is quite low. It's about 20%. And yeah, I think that concludes the normal ULS and buckling check demonstration. I would also like to continue with the fire design. So when you're carrying out the fire design, you have to define a load case called with the value plus fire under the type. So if you go back to the load tabs, go into the load cases, you can see under tab type here that I have a load case. The name of the load case doesn't matter, but it has to be the plus fire type. And this load case is used as a marker to select which of the accidental load combinations should be used for the fire design, because you could have other accidental load combinations for seismic or maybe some kind of impact load or something like that. So to distinguish the fire load combinations from the other accidental load combinations, we are using this load case. It's an empty load case with plus fire as the type, as a marker. When we define this, we are able to go into the fire design. If we go over here and select the CLT panel fire design, we also have fire design for bars, but in this case, I'm limited myself to showing just the CLT. And all the buttons following this selector will change. So in this case, we have different calculation parameters for the fire check. So let's go into them, right click on this member, and here we have the settings for the fire design check. So first of all, the duration of the fire, let's set this to 15 minutes. Then we have, if I want to calculate the beta zero value manually, or use the default value found in the Eurocode. This can vary a little bit depending on annex and depending on the different handbooks that is around. So you can deselect this and set the sharding rate manually if you want, or use the standard value. Then there is a consideration of delamination. So you have delamination is basically when the different layers are delaminating from each other due to either the glue failing or the different layers being very warped, mainly the glue. So you normally use a multiplier on the sharding rate to take this into consideration. And here you can set that multiplier. One multiplier from the top and one from the bottom. We also have buckling length multiplier. So normally you want to increase the buckling length in the fire accidental load case. And here you can set a multiplier for the buckling length. Also, if you want to ignore the stiffness reduction factors or not when doing this, you can read the comment here if you're want more information about this. We also have some standard values for the D0 value, and also if we want to neglect shard layers thinner than a certain amount, and that's normally what you want. So if you have a very, very thin remaining layer after the sharding, having a very thin one layer could be too much on the unsafe side. It gives actually more capacity than it should because the sharding rate isn't exactly uniform, and also very thin layers will probably also delaminate a lot easier. So it's normally you want to neglect shard layers thinner than a certain amount, but it's up to you as an engineer to decide that amount, that thickness. Then we have a protection by connected structures. So you have two options when you're designing the fire protection for the CLT. So you can either have an connected structure or a fire protection. So the difference between a connected structure and a fire protection is that when a fire protection fails, let's say that you encompass this wall in with gypsum boards, and when the gypsum boards fails after like maybe 15 minutes or something like that, you will have a flash fire effect. And this flash fire effect will increase the sharding rate a certain amount of time and then go back to normal sharding rates. This flash fire effect won't be taken into consideration if you have a protection by connected structures. So if I assign this to be like 10 minutes and the sharding starts after 10 minutes, when it starts, it will start at normal sharding rate without any flash fire effect. You can also select like which sides should be exposed to the fire by just clicking on the icon here, like this. Okay. So if you want to assign a gypsum board or something like that, you can go into the manual design, and here you can select, for example, different types of gypsum board or other types of protections. And if I select one, you can see the thickness of this one, or for some of them, you can also set a failure time if you want to define it that way instead. But please again keep in mind that when this fails after this and the sharding starts, it will have this flash fire effect. When I'm done with the settings, both for the calculation parameters and also have defined any protection that I want, I can carry out the check. I can also carry out auto design of the protection if I wish. So let's go into the CLT panel fire design and click on the utilization and go into the magnifying glass. And here we can see the remaining section, the part of the section which has been shard off, and then it's carrying out the check with the reduced panel properties. So it's the same check but with the reduced properties for the panel. And that is the fire design. However, it's still using the forces from the load takedown when it's a full panel. And this, there are no recommendations in the Eurocode that you should redo the load takedown or redo the analysis with a reduced panel size. But if you want to do that, you can do it by just noting the sharding and going back to the structure. You can go back to this type of timber wall and you can create a new one. And instead of 20 here, we had 5 because it was 5 remaining, and you can redo the analysis. But this again is a little bit outside of the Eurocode description. So in Eurocode in general, you are still using the forces from the original section when you're doing the fire design. Okay, so that concludes the design. And at the end here, last 5 minutes before I take questions, I just wanted to highlight different options when it comes to the documentation. So we have 4 overall options depending on what you want, how you want your documentation to look. So you have a list function, you have a simplified documentation method where you do the documentation while you're modeling. A good way is to use the shortcut Control+D. You have a wizard and you have different templates. So let's first go to the list function, show you that real quick. So all the different results, all input and output from the software can be found and be listed as a list. So if we go into tools and go into list, I can select what I want to list. Let's select the entire model. And now I can find different types of materials. For example, here is the inputs, like timber materials, cross-laminated timber types, columns, beams, sections, and so on and so forth, loads, all load combination, load cases, and so on. I also have all results, for example, maximum of load combinations for the characteristic. I can get the nodal displacements or the bar displacements and so on and so forth. And when I've made my selection, let's say I want the bars, I want the bar internal forces min max, something like that. I can click on list tables and it will be sent to clipboard, printer, documentation, Excel file, or text file. So if it's to the clipboard, I can just paste this into an Excel sheet or wherever I want it and have my documentation this way. So here we have that result that I just exported. However, when you're doing the list feature, the documentation will be static. So if you make any changes to the model, you have to do the export again. This can be done by adding this to a batch export. So when I have multiple types of results that I want to list, I can list an entire batch and get that result straight away, instead of having to manually select them every time. You can also save different batches and so on. But again, the result is of course static because the list in Excel won't update unless I update it if I make any changes to the model. That's not the case if I do the documentation inside the software using the documentation module. And here we have an option. If you want to do it a quick and easy documentation, you can just use the shortcut Control-D. You can take any view and just paste that into the documentation. And it can be a view of a 3D view. It can also be like a formula, like maybe I want this formulas in the documentation. I just press Control-D and it's added to the documentation. I can find the documentation module at the top right corner. And here I have first this view and then this formulas. That's a simple way of doing it, and it's suitable for smaller projects. And you can almost create your documentation during the modeling of the structure. The next option is the wizard, and here you can find all different results. It looks quite the same as the listing feature. But you can do filtering depending on a specific story or a specific axis or a user filter or whatever. So let's say that I want to display the translational displacements for this load combination for story number 1. I can do the selection, click on select. Maybe I want for story 2. And now I'm creating a graphical window and I can click apply. And it will create these elements in the documentation like this. And the last option is to load in a template. And these templates can be set up however you want and then just loaded. So you can click on apply and just load in a specific template. And it will, it is basically a structure of a documentation. So it starts out with maybe with a front page, then it's a picture of the structure, then it's a table of content, then it's something about materials and inputs and so on and so forth. And it will create this documentation automatically from that template. So the idea is that you create one template manually first, and then you can save that one and reuse it for multiple projects if you have similar projects and so on. Let me just change the size of the page so you get a basic idea of how it works. I also want to highlight that in version 23, FEM-Design 23, which comes out in the at the end of January, beginning of February, we will have some big improvements to the documentation module in general. So keep an eye out for more information about that. And that concludes this webinar. Please feel free to apply for a trial at strusoft.com or using this QR code. I would also like to just say that we have another upcoming webinar. This time it's how to get started with parametric design in your everyday structural engineering work. And it's in a couple of weeks. So you can register at strusoft.com/webinars. And if you're interested, I will meet you there. Thank you so much for attending this webinar.